Good evening, all. Shall we start now? Hello, can you hear me?
Yes, ma'am.
Okay. So, any of you previously attended the session or you all are new?
New, ma'am. Ma'am, I have attended previously.
Okay. As we discussed in my previous session, that we were doing maths in those phase one. So, as we discussed, I thought of starting it with the material science, and we have already covered phase diagrams. But just now I saw that one of my colleague he's also taking the material science, and he's teaching like his syllabus is uh, more in deep, more in depth. So suppose if you are preparing for XC exam also, so those session will be useful for you. So just today I will give you a brief about materials, and then we will leave the material science and we will start the manufacturing. Okay.
Yes, ma'am.
Did you guys attend the previous session of Jeshuran? 6 to 7 just now. Okay, no problem. We'll start the session, and from next class on the portal it is mentioned the topics of material science, but we will start the manufacturing. So I thought of starting with the casting. You can tell me what subject you want. Like we can jump to metal cutting or casting or forming.
Ma'am, we'll be covering the entire manufacturing.
Yes, yes, I will try to cover. And we have very less time, so today I will take 1 hour only because material science anyway I'm leaving. From next session we will stretch it little bit, and we'll try to cover manufacturing. So I
Can
was
you start
thinking like metal
casting or
cutting.
form?
Sorry,
Can you start with metal forming?
forming. Okay, sure. So from next session we'll start manufacturing. Okay, so let's start this session. So materials. This is the classification of engineering materials. So engineering materials are divided into four categories: metals, non-metals, ceramics, and composites. So in metals, metals again divided into ferrous metals and non-ferrous. Ferrous in which iron will be present, and non-ferrous are the metals like in which iron is not present. Can you tell me other examples of ferrous metal? Someone's mic is on. Can you turn it off?
Okay.
Okay. So you should know about the classification. Then we'll see the non-metals. Non-metals like polymers. Those are actually called as non-metals. Ceramics. Also, like grasses, cement, crystalline ceramics. Then composite. Like you're putting some kind of reinforcement in your metal or ceramic or polymer. The composites are what? It is made of one or more metal, non-metals, or ceramics. That is our called as composite. Any of three uh, are mixed. That is called your composite. More than one substitute. Then again, according to the crystal structure, your material is divided into two categories, basically crystalline and amorphous. What is a crystalline structure? In a crystalline structure, your atoms will be in a serial manner, like they are arranged in a pattern, you can say, or like this. And in amorphous kind of crystal structure, your atoms are not arranged in a periodic manner. It is arranged randomly. Now, what is a can you tell me the difference between crystalline or polycrystalline? Like in polycrystalline, there will be more than one crystal present. Like here, you can tell that this is a single crystal. Only one crystal is present. But here, how many crystals are there? Three crystals are there. Like here, one arrangement, the arrangement is same. The periodicity is the same. But what is difference here? The texture is different. So this is what three different grains. Why polycrystal is found? Suppose you're melting something, you're melting a metal, and then you started a solidification. So how solidification starts? Solidification starts from the boundary, or if some impurities will be there, so it will start like that. Some, suppose here also some impurity material is there. I will teach you in casting how solidification phenomena is work. Suppose one grain is forming here, one grain is forming here, one grain is forming here. So since it is a crystalline structure, all the grains will be, atoms inside the grains will be arranged in a periodic manner only, same manner, but their orientation, their texture will be different. So that is why if you can say more than one grains, more than one type of grain is present, if grain boundary is present, that means that kind of structure is a polycrystalline structure. Suppose there is one single grain. What we do in manufacturing, one single grain also we call as a crystal. Okay, so sometimes don't get confused between grain crystal and polycrystal. Lots of
What's up?
yes. Okay. Then there are a few small definitions that you should understand. First is a unit cell. What is a unit cell? So a crystalline structure are built up by a small group of atoms which are repeated in the entire material. Okay, so this, suppose this is your crystal lattice. This is your crystal lattice. Since what is it? It is a crystal. That means there will be some periodicity. There will be some repetition in the distribution of the atoms. That is what a crystal. So that smallest cell which can represent the whole crystal lattice, that is called as unit cell. Suppose this is your crystal lattice. So in this small cell can represent. Suppose if you start repeating this cell in the space here or here, here, so your lattice will form. So this small cell is called as unit cell, which can represent the whole crystal lattice. Okay, and these points at which uh, what we assume in the material science, that our atoms are spherical. Okay, is they are sphere and they are sitting at the edges, at the points of the unit cell, and those points are called as lattice point. Okay, so according to the arrangement, according to the periodicity, there are 14 types of arrangements by which 14 types of arrangements by which atoms can be arranged in a crystal structure. So suppose some metal is there. Let me take what metal we can. Let me take lithium. Okay, lithium can be found in metal form also. So lithium has a BCCA structure. What does that mean? That means that the atoms inside the lithium will be arranged in this manner. There will be 4 atoms here, one single atom will be here, then again 4 atoms will be there, and this is what? This is unit cell, and then we will repeat this manner throughout the space. That will be the lattice of the lithium. So that is how there are 14 arrangements in which atoms can be distributed. So these 14 arrangements are called as Bravais lattice. Okay. So what are those arrangement? There are 14 like simple cubic, face-centered cubic. I assume that you all already heard about these things and you all already know. So we are not going deep into it. Then simple tetragonal, BCT, HCP, SO, BCO, BCO, face-centered, rhombohedrals, monoclinic, triclinic. There are like 14 kind of arrangement in which atoms can be arranged in a lattice structure. So what are the primitive and sometimes I have never seen any questions in GATE on these topics. So these are not that important, but these are your base. So you should at least know about because when you go for casting or informing also, these things are useful. Material science is useful for casting and forming also. So why we read the material science? Because whatever the properties you want from your material, that solely depend upon the crystal structure. So BCC will show a different property, FCC will show a different property. Suppose you want to do some project and some kind of property is required. So you should know what material will give that property and what structure will give that property. Arrangements of atoms are very important because their properties are solely depend upon how the arrangement is being done. Now, these two words also you should know, primitive and non-primitive. So primitive unit cells are those cells in which atoms are only at the corners. Like simple cubic is a primitive. Here orthorhombic, simple tetragonal, these are primitive cells. Where the atoms are present other than the corners also, like in FCC, like in BCC, those are called as non-primitive. Okay. So one more thing which is also required to know, uh, to define a lattice is firstly this length, the length. I have taken a simple cubic. Suppose this is A1, A2, A3 and the angles between them. Alpha, beta, one more angle will be there, gamma. So these things is called as lattice parameters. So what you should know about a crystal structure, like what kind of unit cell they will have and what will be the lattice parameters. So according to the lattice parameters, there will be 14, if you'll count these numbers, there will be 14 type of arrangement which are called as Bravais lattice. Any doubts till now?
No,
Okay. So next, these things, the table.
ma'am.
Yes,
Excuse me, ma'am.
yes.
The seven type is unit cell, right, ma'am?
Yeah, seven type
The
of unit cell, 14 types of arrangements.
yes, ma'am. Thank you.
Okay. So now this is the table that which is actually important, which actually you should learn. And sometimes they will ask question from this, like they will ask you about the any of these things they can ask. Even in the interviews when you'll go after getting good marks in GATE, you'll being called for the interviews. So these kind of things, if you will tell them that they'll ask you what kind of subject you know the best and you will say material science or anything related manufacturing, so they will start asking. First question they could ask about the coordination number or maybe a packing fraction. So this table is actually important. So what are the elements present in the table? First, number of atoms per unit cell. Okay, so your unit cell, we suppose one unit cell I'm drawing here. This is what let's draw a simple cube. There will be a atom. This is not a circle. This is a sphere. There will be one more atom. Okay, this is your simple cubic structure. So your atoms are actually sphere. So what you have to do, you have to imagine, yes, you have to imagine what are the how much atom is present on the lines. So here is what 1 by 4 of a sphere, 1 by 4th of a sphere, 1 by 4th of a sphere, and 1 by 4th of a sphere. So what is this? This is one atom in present in a unit cell. So for that is how for simple cubic only one atom is present. Then the coordination number. What is a coordination number? It is nothing but number of nearest neighbor possible in a unit for a atom. Okay, then the packing fraction. Packing fraction means how densely your atoms are packed together. Like how dense are there, how near are they. So that is called your packing efficiency. So here or packing fraction. Here you can see that the FCC and HCP both have, this is what? Diamond cube. FCC and HCP, they both have highest packing efficiency. That means in these kind of crystal structure, the atoms will be closely packed. They will be dense. They will be very near. Simple cubic, it is 52, BCC 68. So these kind of like properties also will give this kind of not properties, these kind of you can say inherent kind of things will also give you a different property. Sometimes you will need a material which is closely packed, and you should know that thing will give you what property, that we will see in later slides, that where why do we need these kind of how why do we need to know about number of atoms or coordination number or packing efficiency. Okay, so let me show you how we are calculating. So what I was telling, you can sorry,
Ma'am, what is DC?
this is diamond cubic.
Oh, okay.
Okay, one question I have seen in the gate previous exam, what they can ask, they can suppose they will give you 4 or 5 metals. Suppose one is magnesium, then lithium or aluminum and zinc, or let's say silicon. So they will give you 4 or 5 metals, and then they will write the different crystal structure, and they will ask you which option is correct, match. So that you should also know, not you cannot learn for all the metals, but at least these kind of metals you should learn that they have what kind of crystal structure. Okay,
Madam,
yes,
ma'am, how look like a DC, ma'am?
sorry,
Please draw the DC structure, ma'am.
DC structure you want me to draw?
Yes, ma'am.
Okay,
And actually, diamond cubic is modified FCC only.
sorry,
Diamond cubic structure is modified FCC only.
yeah, you can say that.
So the properties being so different.
As he said, it is somewhat like FCC only. In FCC also we have atoms here. But like have you seen HCP? Like in HCP there will be one more plane of atoms in between. Same like the in the diamond crystal type of also there will be one more plane of atoms which will be having like one here, you can say one here, and one in this plane. One more kind of plane will be there which will be having four more atoms. You have seen HCP crystal structure, like it will be like one hexagon will be there. Make it hexagon. Suppose this is hexagon, and one more plane will be present of three atoms in between. That is your HCP. Same like in the DC, it will be kind of FCC only. One more plane of atoms will be exist in between. Okay.
Okay.
Okay. In these GIF, you can see how we have calculated how many numbers of atoms will be present in one unit cell. Like, can you tell me which crystal structure is this?
BCC,
This one.
FCC.
This one.
Simple cubic.
Yeah, simple cubic.
One
We have seen now, like one atom in simple cubic, two in BCC, four in FCC, six in HCP, and then when I went for an interview, na, the first question they asked me was how many number of atoms is present in BCC. So this is very important. Even if you don't remember, you should know this logic, what logic we are using, and you should remember how many atoms on crystal structure is having. Okay, anyway, I will share the notes in my drive. You can go through that. Okay. Now, atomic packing factor and coordination number, as we have already seen. This is, can you tell me which lattice is this?
Body centered cubic.
Okay, good. And which one is this?
Face center.
Right. So this is nothing. This is the diagram I added in this presentation just to show you that how do we calculate the nearest neighbors. Okay, so BCC has 8 nearest neighbors and FCC has 12 nearest neighbors. Now here also you can feel that why BCC is more dense or more packed structure. You can see its neighbors also like 12 nearest neighbors. Sometimes if you are not remembering which will have more nearest neighbor, you can check like that, because FCC and HCP are more closely packed structure. So they'll have one atom will have more nearest neighbors. That is why FCC is having more nearest neighbors than the BCC. Okay. Now we will see how to, like, here what else was present, packing fraction. So now we will see how to calculate the packing fraction. So I'll do for simple cubic and BCC also, FCC maybe. Then HCP you try on your own. So what is a packing factor? Packing factor is volume occupied by the atoms in a unit cell divided by volume of whole unit cell. So this is your simple cubic. This is your simple cubic. We'll cut one plane. Okay, we'll cut one plane, and suppose the radius of the sphere is r, and your lattice parameter, which is this length, is a. So firstly what we will do, we will calculate the number of atoms. So there are one atom in unit cell, and you have to find the relation between A and R. So that will be, this is also R, this is also R. So A will be 2R for the simple cubic. Now volume occupied by the atoms in one unit cell. How many atoms are present in this unit cell? That is one only. And volume of a sphere, volume of atoms. Volume of sphere is 1 4 by 3 pi r cube. Pi r cube, we can write it as 4 by 3 pi r cube. Then the volume of the unit cell. So your lattice parameter is A, so your volume of this unit cell will be A cube, which you can also write as 8 r cube. Now what you have to get the APF, atomic packing factor, will be 4 by 3 pi r cube divided by 8 r cube. When you calculate this, it will be coming as pi by 6. Then you will multiply, it will be 0.52. So APF of your simple cubic structure will be 0.52. Next, calculate for FCC. So in FCC, number of atoms will be, I'm directly writing that number of atoms is 4. Then the volume occupied by atoms will be number of atoms multiplied by the volume of the unit cell. Okay, now we have to calculate the relation between lattice parameter and the radius of the atom. So it will be like so in the phase cubic, this plane will contain one more atom. So when you will calculate the distance, like figure, this height will be root 2a, or you can say this will be 2r. Suppose this is no space, this will be 2r, and when you will calculate this, your relation will be root 2 is a is equals to 4r. Okay, then your volume of unit cell will be a cube, which will be 4r by root 2 to the power 3. So your APF will be 16 by 3 pi r cube divided by 4r by root 2 power whole cube. When you calculate this, again it will be coming as 0.74. Same for BCC also. What you need to know is the number of atoms that is present in one unit cell. So for BCC, number of atoms that is present in one unit cell, 8 on corner multiplied by 8 plus 1 in the center, that will be 2. Then the volume occupied of one atom will be number of atoms divided by 4 by 3 pi r cube. I'm not explaining these things much because I'm assuming that you all already know all these things. These things are not important. Like derivation is something which is not very important. You just should know the value. Sometimes those kind of question only they will ask in your gate examination. That will be 4r divided by root 3 to the power 3. So your APF for BCC will be 8 by 3 pi r cube divided by 4r by root 3 to the power 3. It will be around 0.68. So that is how you calculate the packing factor. Now for HCP's crystal structure, you can see it is already very complicated. So its calculation for APS is little complicated, which is also not in your syllabus, but you should know properties about HCP crystal structure also and the APF for the HCP. So for simple cubic, your APF will be 0.52. Then we'll go for to BCC 3.68, and the both closely packed structure FCC and HCP, that is 0.74 and again 0.74. Okay, this is the table. So this you should learn. You should get to know about more metals which are having BCC, which are having FCC or HCP, that you should know what metals or what materials are having what kind of crystal structure. Then one more thing that I want to tell you about.
Ma'am, what is DC written on the
Sorry,
DC?
DC is diamond crystals, diamond cube. Okay, one more thing that should learn is mechanism of solidification or crystallization. Okay, so when the transition from liquid state to solid state takes place, firstly what happens? One nuclei will form. Okay, one small, suppose this is your molten metal. So one small nuclei will start forming. Then those nuclei will start growing. That is called formation and growth.
Great.
Yes, growth of a nuclei. Uh, can anyone tell why these things happen?
मैम टेम्परेचर डाउन हो रहा है तो पार्टिकल पास पास आते हैं.
Correct. But it is not like not just because of the temperature. One more phenomena which is involved in
But
this, that is called free energy.
फ्री एनर्जी. हाँ.
Yeah, gives free energy. So solidification starts because of that phenomena only. Which phase will form, that will also be defined by Gibbs free energy. So those things are already mentioned in Callister book, but that is not important for your GATE syllabus. So mostly what is important in the manufacturing and material science doesn't have much weightage, but at least you should know more about phase diagrams, and heat treatment is also very important. You should know about these crystal structure defects and HKL and all. So those things I was thinking to teach you, but Jashuran will teach in his class.